All right, yesterday we learned about NAND gates as universal gates. Today we're going to learn about the NOR gate. All right, so we're going to talk about the basics of what a NOR gate is. We're going to talk about how they can replace an AND, OR, and an inverter gate. And then we're going to talk about how do we actually take an AOI circuit and redo it with NOR. And then finally looking at, once again, why it's important to use a NOR gate to replace those. Now, with that being said, quick side note, okay? The NAND gate is the more popular. Why? Because it works with SOP. And SOP, as we already know, is more popular, okay? However, NOR gates work well with POS, which on occasion is quite helpful. All right, so with that being said, let's move on. So here it is in all its glory, the wonderful NOR gate, okay? Unfortunately, not as popular as the NAND. He'll survive. All right, or she. Don't want to make any assumptions here. All right, so anyhow, we have an OR followed by an inversion. That's our little bubble there. All right, so with that happening, we get X and Y coming in, out comes Z, okay? Which in this case, since it's X and Y, it's X or Y with a bar all the way across the top. Break the line, change the sign. Don't know why my sign's not showing. That should be an and there. All right, I guess it doesn't need to show, but I don't know why it looks funny. So essentially, if we look at the truth table here, this would be the opposite of an OR gate, okay? Because technically that would be a 0 if this was an OR gate, 1, 1, 1, okay? But this is obviously the inversion, hence an OR gate followed by an inverter. So now let's look at how it inverts. Okay, same thing here as a NAND gate. So this one isn't very complicated. All we have to do is take whatever it is we're trying to invert, run it into both of the inputs, and the output will be the inverted version of the input. Not too complicated. Now, getting a little bit more complicated, if we want to create an OR gate, we have that inversion, that bubble there occurring at the end. So all we have to do is invert it again, which we just learned how to create an inverter out of a NOR, and we will come back to a regular OR gate. So see how this is just X or Y with a double inversion? Cancels out, leaving me with X or Y. Okay, and we end up with what would be the equivalent of an OR gate down here. And if we want to create an AND gate, we need to do X and Y through an inverter first, and then we're going to take the inverted X and Y and run it through a NOR gate, okay, which ends up with not X or not Y, all of that inverted. Break the line, change the sign, following De Morgan's rule, okay, or theorem, and we end up with double inverted X and double inverted Y cancels out, X and Y, and essentially this is the equivalent of an AND gate. Beautiful. So what does this mean? This means just like the NAND gate, we can replace each one of the AOI gates with NOR gates. And the process is much the same for this too. We're going to first create the AOI, take the AOI and identify each of the replacements, the NOR equivalents, redraw the circuit with the NORs. Then for this one, again, we haven't quite talked about, but we did talk about with NAND, eliminate any double inversions and then redraw the circuit. Don't be lazy and just exit out, redraw it. All right, so here's a very basic AOI circuit. We got B and not C, or A and C. We're going to take each one of those gates. We're going to identify the equivalent NOR gate. All right. Then we're going to take those NOR gates and replace them out. Beautiful. All right. So this is what it would look like. Now we're going to check for double inversions. Now what we started with was an SOP circuit, right? We started with a statement. Okay. So notice there is only one double inversion here. Okay, it was not quite as successful as the NAND version of this. Okay, but we still have our double inversion. We could still cancel those out. Okay, which leaves us with this guy. And if we do a gate analysis, they're going to show you it's the equivalent here first, okay? But at the end, our statement is still the same, B or not C, or sorry, B and not C, or A and C, which is equivalent to what we started with. All right, to the gate analysis now, which I was getting excited about there. Okay, we started out with 3 gates as just like last time. We had to have an inverter, an AND gate, and an OR gate, which left us with 3 ICs. Now this time we were successful in trimming it down to 2 ICs because we still have a total of 7 gates, which would require 2 NOR ICs, which is the 74LS02. However, it wasn't quite as successful as the NAND gate. Okay, like I said, the NAND gate is way more successful with a POS statement. Now, once again, if there was anything in this presentation that you did not understand, please, please, please see your instructor. They will be more than happy to help you. All right, have a good day.